maybe we can find the wave pattern, some function in X, Y, and Z in 3D that tells us the probability of what the allowed wavelengths are and where the particle is likely to be. So what that is Schrodinger's equation, Schrodinger's wave equation for electrons around an atom. It's called a wave equation because it describes the way a wave behaves for electrons around an atom. And what it is exactly this description of which wavelengths are possible in 3D. Now in 3D, the concept of wavelength is a little more complicated because it has wavelengths in multiple directions. So this is what it looks like. Let's look at the components. So that h bar squared is Planck's constant, you divided by 2 pi. The m is the mass of the electron. And this is Coulomb's law. So where is this coming from? This is the mass of an electron. This is the mass of an electron around an atom. And therefore, it's feeling a potential energy. And then, so if you have some function here that essentially describes the wave of the electron in 3D, operate on it with this part, you take all the second derivatives there, and then you add the potential energy times that function. Again, it gives you the energy of that electron. So what this is, yeah, and so R vector is the location in space, and E is the energy of that electron. So you have the wave equation, and this is a differential equation. The solution to a differential equation isn't a single number, it's a function. So what you do is you solve this differential equation using methods of differential equation solving. It's actually a partial differential equation, so it's kind of hard. You solve the wave equation, and what you get is a set of wave functions and corresponding energies. There's only some functions that match, and those functions are exactly the functions that have the right wavelengths. And each function corresponds to an energy, and that energy is the energy the electron has. And so you have the corresponding energies and the wave functions. And it turns out that the probability of finding an electron in a region of space is proportional to the square of this wave function that you get out. So that is the key. There's some deeper things you can see right off. If this is the potential energy, here's the potential energy of the electron. The potential energy due just to Coulomb interaction with the nucleus. It should be more clear that Z here is the nuclear charge. E squared is the charge of the, so E is the charge of the electron and ZE is the charge of the nucleus. Then, and K is just the constant, the proportionality constant in Coulomb's law. This is the potential energy. It turns out that for a wave, this is the kinetic energy. The kinetic energy of a wave is related to essentially how wiggly it is in space. You know, the dx, which has how wiggly it is in the x direction, dy, how wiggly it is in the y direction, and dz, which is how wiggly it is in the z direction. So really, you could see in a weird way that sort of like the kinetic energy plus the potential energy is the total energy. This is far more than we can get into, but that is sort of the content of the wave equation. Okay, so you are not going to be expected to solve this. This takes, you know, this is, you get into solving this at like, you know, the last half of an intro quantum mechanics class. We're not going to solve it. But you should know what the content of this is, that you essentially have an equation that says if you have the wave of an electron confined around a nucleus where we know the energy, the binding energy that's holding it into that, there are only certain patterns of waves of electrons that are valid, and this is the equation. If it satisfies this equation, it is a possible solution to that. Okay, so that is Schrodinger's equation. Let me add a little bit more about probability. So for a classical trajectory, you know, it starts in one place, it goes to the other place. For a quantum mechanical trajectory, you get something that's more smeared out. And it turns out that this wave function squared is the probability of finding a particle at the location X, Y, and Z. So that's what we're getting at. What we can't really measure the wave function directly. What we can do is calculate the probabilities of finding a particle in that area by squaring it.